Hey guys, today we're going to do some notes with projectile motion. You've already taken some notes with your projectile motion web quest, but we're going to kind of put it together because we're getting ready to do a lab and solve some numerical problems. Okay, so first of all, we're going to analyze the motion of a movie here. We're going to look at a basketball shot. Now, you've seen me use this before, and we're just going to kind of use it again to look at an object in projectile motion. So let's just go ahead and analyze this motion. I'm going to start by setting a scale, and my scale is shown here in this picture. That's actually 2 meters, so I'm going to mark that as 2 meters. And that just tells the computer it's going to be able to, we're going to get a graph of its horizontal and vertical motion. You should know by now that with projectile motion we have 2 components of motion. We're dealing with 2 dimensions here. So I'm going to just go frame by frame, and we're going to mark this object each frame, and we're going to get a pretty cool graph, and we're going to kind of analyze that graph. So at this point, I know it's blurry, but the basketball is out of his hands, so it's considered a projectile then. All points before that, while he's holding the ball, it's not a projectile because his hand is touching the ball, and so his hand is actually providing a force. So I'm just going to go through here. We're going to take it frame by frame. I'm marking its location. You can see I'm marking the center of the basketball for each frame. Now you can already tell that we're going to start curving, so look at what's happening. It's slowing down as it goes up. If you refer back to that cheat sheet that you have, then you'll notice that its motion is the same as slowing down as it goes up, and then it starts to get steeper, so it's speeding up as it comes back down. And you'll notice we got the dots were really tight up here, and now they're spreading out even more. So we're going to look at a graph here in a minute and see what that means. So I think that's all we're going to do, because after that it's no longer a projectile. So let's look at our graphs now. I want to go ahead and analyze this motion. So looking here, you'll see that there are 2 parts of our motion. The first component of our motion is represented with an x, and just like in math, an x-axis is your horizontal motion. Okay, in this case we're talking about horizontal position, okay, horizontal displacement. Now the y graph that we see in blue here, now we're dealing with 2 dimensions, so just in math, like on an x and y axis, now we're talking about the motion of the object up and down, okay? So, right off the bat, we can look at our x motion, and I could draw a line of best fit through a majority of these dots. Now, that tells us something important. Because this is linear, that tells us that the horizontal motion is constant. Nothing is changing about the horizontal motion. It has a constant speed, or we would say a constant velocity. Constant velocity. Now, if I wanted to, I could find that constant velocity. We might look at that in a second. Now, the vertical motion is curving. So we're going to be putting our last 2 units together when we're talking about projectile motion. The 2 units ago, it was our constant velocity unit. Notice we have a horizontal position and time graph that is linear, indicating a constant velocity in the positive direction. And we know that with the basketball, it always moved to the right. So it was always moving in the same direction. So it had a constant velocity. Also, there's no horizontal force. That's why it has this constant velocity. Because if you remember from your web quest and the definition of a projectile, the only force acting on a projectile is gravity. Now, gravity acts up and down, so the only motion that we should see changes in is the y motion, and that's where we see gravity causes this parabolic trajectory. So what we see at first is the object slows down. Okay. It slows down, and then eventually at the top of its path, it reaches a zero velocity. Okay, it stops at the top. Now, it's only stopping vertically. Okay, it keeps moving to the side. That's why it has this horizontal speed, but it stops on its way up, and then gravity causes it to speed back up on the way down. So here it's speeding up again. So it slows down, comes to a stop, and then starts to speed up. And that we see our vertical motion changes. Okay, or our vertical motion acts like an object in free fall. So it slows down, stops, and then speeds up. So its motion is accelerating. Okay, we see some acceleration there. All right, let's look over here. We're just going to go back to the screen. All right, so let's kind of put this in a table here. So first off, let's deal with our horizontal motion. Okay. Horizontal motion we call the x direction. Now, what we said from the basketball shot, we saw that it was linear, so we're going to say that it moves with a constant velocity. The reason it has a constant velocity is because of Newton's first law. First law of motion. There's no horizontal forces. Or no x forces. And remember, inertia says that things are going to keep doing what they're already doing. So in this case, if an object is moving horizontally, it wants to keep moving horizontally. The only reason the path of that basketball changes is because of gravity, and it's changing up and down. So in this case, because it's a constant velocity, we only have one equation that we can use, and that's the equation for constant velocity. Velocity equals delta x divided by time. Now, I'm going to rearrange this a little bit. Okay, delta x we're going to call the range. So I can say that delta x, or my distance, the range, how far that projectile travels, is given by our horizontal velocity. Now I'm going to put a subscript x here to show that we're just talking about the horizontal motion, because now we're dealing with two dimensions. It's moving up and down, and it's moving left and right. So delta x equals Vx times time. And let's just go here. I'm going to write down what these stand for. So I'll use black. We know that delta x is a horizontal displacement. It's how far the object travels. Okay. T is time. And Vx is a horizontal velocity. And this is the only equation that we can use when we're talking about the horizontal motion of that projectile. Now let's look at the vertical motion. It's going to be a little different. The vertical motion we treat as y, just like on an x and y axis. Now we're talking about how the projectile changes as it moves up and down. So in this case, it didn't move with a constant velocity. It actually curved, and it had a parabolic trajectory just like an object in free fall. So this acts just like an object in free fall. And that's because gravity is acting on it. Acts just like an object in free fall. So if we take our last two units, where we had a constant velocity and free fall motion, and we put them together. Now we have an object moving in 2 dimensions at the same time. So free fall motion, we had a few different equations that we could use. We know that now gravity is affecting it, and gravity is making its speed change by about 10 meters per second every second. Now remember that negative is because gravity pulls things down always, okay, in a negative direction. That's why when we oppose gravity going up, we slow down, and when we go with gravity on our way back down, we speed up, okay? Now, I'm going to write a few equations here. The first one is G equals the final velocity in the y direction. Now, our velocities are changing, minus an initial velocity in the y direction over time. This is our main equation here. Acceleration, that's what G is. Okay, G is the acceleration due to gravity, equals our change in velocities, but I have to put a y here now because we're talking about just the vertical motion. We don't have changes in velocity when we're talking about horizontal motion. All right, our second equation is delta y. This is a height equation. Delta y equals 1/2 gt squared plus our initial velocity in the y direction times time. There's our second equation. And then finally we have one more equation. Vf squared equals Vi squared. Now I need to put y's on both of these because we're talking about just the vertical direction now. Plus 2 times G times delta y. Now, delta y and delta x are different. Delta y is a vertical displacement or a change in height. This is a horizontal displacement, also known as range. This is a vertical displacement or a change in our height. T, of course, is still time. G is what we call gravitational acceleration, the acceleration due to gravity, okay? VIY is our initial velocity in the vertical direction. Let's see, initial vertical velocity. Initial vertical velocity. The Fy then is a final vertical velocity, and I'm just going to put an arrow here. We're going to have final and initial, so I'm just going to put a slash here. Those are initial and final speeds. And at that point, I think we've defined all of our variables. Now, there is one variable that is the same in both of these. Here we have time, okay? And in all of these equations, we have time, and those connect. Time connects the horizontal velocity or the horizontal motion to the vertical motion. Those are connected by time because time goes across everything. Now, I know this is a lot. Go ahead and write it down in your notes. We won't be using all of these equations, but it's good to understand that we have two sets of equations now to deal with these types of problems. Our vertical velocities can change, and our horizontal velocities can change. So, let's look at an object's trajectory. Now, we know, I'm going to plot a few points here. Let's say these are the points of a trajectory here. I'm going to just move myself here. We're going to go through and we're going to draw the horizontal and vertical motion for both of these. Okay? So when something is thrown, okay, we're going to have a constant horizontal velocity, which we call Vx. It doesn't change. And again, it doesn't change because there's no horizontal force. So I'm drawing all of these arrows the same size. So this red arrow represents Vx. Okay. Now, my vertical velocity is represented by Vy. Now, what happens over time is that we see Vy actually gets a little smaller. Okay, Vy in every case gets smaller, except right here, Vy equals 0. There is no vertical speed. It's reached its maximum height. It's no longer moving. So now it's going to change direction. And we see what happens down here is that it starts to speed up again. So these arrows, these vectors I'm drawing, represent the speed of the object. And then it gets a little faster. And I'm going to put some congruent lines here. So this guy is going to be the same speed as this one. That one is going to be the same speed over here because we're at the same position and everything is symmetric. And down here, we're going to have a final speed that is congruent to this one. Okay. Now, if I wanted to draw my overall speeds, this is where those rectangles are going to come back to haunt you. This shows you the overall speed at a specific point. I'm going to draw a rectangle, and we'll see that these arrows are getting smaller and they're changing direction. So that shows you that we slow down as we move up. Okay. And then we start to speed back up as the object comes back down. Now, I did not draw an arrow up here because it's only my horizontal velocity, so I could have just drawn an arrow like that. My overall velocity, it doesn't have a component. I can't draw a rectangle with one arrow, so I don't draw a rectangle in that case. And finally, it hits the ground right about right there. That's the final velocity. All right, so again, what we see, vertical velocity changes. Our horizontal velocity stays the same. Now, looking at this, let's look at an example here. Let's say every dot or between dots represents 1 second. So it looks like I have 1, 2, 3, 4, 5, 6 seconds total. So if I have 6 seconds total, that means I launched it vertically at 30 meters per second. Because remember, our velocity changes by about 10 meters per second every second. So after we go up again, we're going to be moving at 20 meters per second. We lost 10 meters per second here, minus 10. Okay. Now, if we lose another 10 meters per second, my vertical velocity is now 10 meters per second. And if I lose another 10 meters per second, I reach 0. Okay, so my vertical velocity is 0. I'm only labeling the blue arrows, my vertical speed. Now, let's gain 10 meters per second. And that negative is just the direction. So right here, my velocity is negative 10 meters per second. Now we're gaining speed. We went from 0 to 10. And again, that negative is just direction. So now in the next second, let's use our acceleration and gain another 10 meters per second. So now my velocity is negative 20 meters per second. And now we can gain even another 10 meters per second in the same direction. So we end up moving at negative 30 meters per second after 6 seconds. Okay, now I'm just going to give you a bogus number here. Let's say that my horizontal speed was 20 meters per second. Well, because there's no horizontal forces, that means that I'm 20 meters per second everywhere. So right here, Vx equals 20 meters per second. Right here, we have 20 meters per second. So everywhere. Now, with that being the case, now that I know my x and y, we're going to do what we were doing in the very first unit, and we're going to be able to use Pythagorean's theorem to find the overall velocity. Now, I'm not going to do it for every part, but we could find the velocity at every point. So our velocity squared equals Vx squared plus Vy squared. Our overall velocity V is going to equal Vx squared plus Vy squared. Okay? So let's just look at this guy right here. I want to know my overall initial velocity. Well, I have 30 this way, 20 this way, and I am trying to find my overall velocity V. So I'm going to say V squared equals 30 squared plus 20 squared. And when I do that in my calculator, I will get V squared equals, I'm just going to do this really quick, 30 squared plus 20 squared. V squared is going to equal 1300. And to get rid of the square, we have to square root both sides. So now I can say my total velocity is the square root of 1300. All right. Now you guys are going to have a problem where you have to draw the Vy at every point, and you have to draw the Vx at every point, and you have to find some of the overall velocities. So the diagonal here, that's your total velocity. Okay? That is just plain old V. But when we're talking about projectile motion, Vx and Vy work together to get your overall resulting velocity. Now, I know that was a lot, but I hope it helps you on your next worksheet.